Good afternoon, everyone, and thank you for joining us for today's webinar. My name is Jean-Pierre Picard. I'm Product Marketing Manager at CM Labs, and I'll be your host today. With me on the line is Marc-Alexandre Vizina, Product Manager for Vortex Software Solution. He'll be handling the live demo portion during today's presentation. Today's topic is Vortex Vehicle Systems, and our presentation will last approximately 40 minutes, and we'll finish with a Q&A. Now, this webinar is part of Vortex University. If you're not familiar with Vortex University, it is a monthly simulation webinar series where we talk about a single topic and dive in depth every month. Now, you can keep track of upcoming sessions at the address you see on the screen. Please be aware that we're taking a break for August because everybody is going away on vacation, and we'll be back for the next presentation in September. If you're joining us but are not familiar with Vortex, Vortex is CM Labs' real-time visualization and simulation solution. It's used worldwide for different types of tasks, such as virtual prototyping, in which an engineer creates a virtual rendition of new equipment design and tests its performance in simulated environments. It's also used extensively for operator training and operational planning. Vortex is used as the basis of simulators that immerse operators and trainees into lifelike visuals and allows them to practice common or uncommon movements and get ready for specific assignments. So I mentioned that Vortex Vehicle System is a module of Vortex Software Solution. What we mean by that is that it provides additional capabilities beyond Vortex Multibody Dynamics Engine. What it does is it allows you to create and simulate vehicles in real time, and those vehicles can be wheeled or tracked vehicles. The main difference with Vortex is that you simulate vehicles based on engineering specifications. So you will get very accurate performance, and you'll be able to discover emergent behavior based on specifications, not on pre-coded performance and effects. Today's presentation will be split in a few sections. The first thing we're going to look at is vehicle presets, which is something you find in the Vortex editor. We're going to present what they are, why they are useful, and how you can create your own vehicle presets. Then we're going to see how you can use them to define a vehicle's architecture, and we'll move into the biggest portion of today's presentation, in which we'll model a vehicle from start to finish. Specifically, we'll be modeling a military vehicle, a light armored vehicle with 8 wheels. For those of you who have a Vortex software solution installed, it's the LAV provided in the samples with the software. We're going to close off the presentation with a discussion about how you can combine vehicles with cables and earth-moving simulation to create more advanced vehicles for specific simulation scenarios. Now, if you have any questions during today's presentation, or if you have issues with audio or visuals, I invite you to use the right-hand side questions box. We have people on the line waiting for your questions that can take them in real time. We'll also be doing a live Q&A at the end of the presentation. You can also download today's presentation using the handout section, and you'll also notice that we've included 2 data sheets, the first one on Vortex Vehicle System, the second one on Vortex Editor. The Vortex Editor is the application we'll be using during today's live demo portions. It's used to create, validate, and deploy Vortex simulations, and as well as Vortex equipment and scenes. All right, so let's jump into it. We're going to start by talking about vehicle presets. Vehicle presets exist because when you want to simulate a vehicle, you first have to define a vehicle's engine architecture. Now, not all vehicles are the same, and it's evident if you look at the breadth of vehicles that have been simulated with Vortex. Some of them, such as today's light armored vehicle, are military vehicles with multiple axles and very specific designs. Now, other vehicles will have tracks, such as a tank, and obviously when you want to model that tank, you're going to be needing parameters that are different from the LAV on the left-hand side. But Vortex has also been used extensively to simulate heavy machinery, such as excavators, and these will have, for example, very specific types of components, an hydrostatic transmission, for example. Vortex has also been used to simulate more complex and, let's say, unique vehicle systems, such as the forwarder, which is also included in Vortex sample. This is a vehicle with 2 chassis. So all vehicles are different. You cannot use a cookie cutter approach to creating a vehicle simulation, obviously. But there are still components that are always going hand in hand. For example, if you have an automatic transmission, then you will have to also specify the torque converter performance. Now, if you were to use a manual transmission, then you'll have a dry clutch component. So instead of starting every time from scratch and creating every single component you're going to model, vehicle presets allow you to take a predefined set of components, and it also predefines the relationships they have to each other. So this saves time, makes everything more efficient, and prevents errors as well. Now, you have a library of 14 presets out of the box in the Vortex editor. These cover a very wide range of wheeled and tracked vehicles. But you could also create your own customized presets, and we'll show you how in a few minutes in the first live demonstration. Now, these presets add the necessary input, outputs, and parameters to your mechanism. So if you select, for example, the all-wheel drive car preset, then you would populate your mechanism with transmission, with engine, and wheel inputs, outputs, and parameters. Now, this is a internal combustion engine, so you would be defining the performance of the engine based on torque table and then the distribution through the transmission and differentials. But if you were to use the PackBut preset, and a PackBut is a small electric explosive ordnance disposal robot, then you're going to have very different inputs and outputs. You can see that there is a much smaller list of inputs that are mostly focused on the electric motors that are governing the left and right side of the tracks. You also have different outputs. So in this case, you have tracks instead of wheels. So presets are a way to quickly build that list of inputs, outputs, and parameters based on existing designs that include all the necessary components. So before we jump into the editor and look at how you can select a preset and how you can customize a preset, we'd like to talk first about the different components that are included in those presets. The first component, obviously, is the engine. As I've already mentioned, you can model two types of engines in Vortex vehicle systems. The first one, the internal combustion engine, is the type of engine that you see in most vehicles out there. In cars and AV equipment, it's a gasoline or a diesel type engine. The second one is an electric drive, which you see more and more, and you see especially in the robotics world. Now, regardless of the type of engine you choose, you'll have to provide data to model the engine. So you'll have to provide a torque table, but you also have to define the response delay of the engine. You also need to define the drive shaft and its friction, because Vortex simulates the engine using the torque table and the drive shaft. And you have to also define the throttle that is fed to the engine. In terms of outputs, your engine will provide horsepower or power to other components in your vehicle, and also a current RPM. Vortex also allows you to simulate the transmission, and there are three types of transmissions. The first two main ones are automatic transmission and torque converter, or manual and clutch, but you could also simulate an hydrostatic transmission. We'll look a bit at those as part of our live demo in a few minutes. Now, on the inputs and parameters side, if you model a manual transmission, you'll need to provide gear ratios. If you want to model a automatic transmission, you'll need to provide some more information, such as the gear transition time, the control and lambda tables, which can be set up as external files that are linked inside a simulation, so that is extremely convenient if you're exporting those tables from a engineering simulation solution. And if you have a automatic transmission, you also need to provide the RPM at which the transmission will be shifting. Now, you can model more advanced transmissions, such as a dual clutch transmission as well, using advanced fields, which we won't be covering today, but you'll be able to set this up in vehicle systems. Up next is the differential. So Vortex allows you to simulate open differentials, which you find in the majority of vehicles that are used on roads, but also limited slip and lock differentials, which are very useful for off-road vehicles, such as military vehicles. You need to define the gear ratios of your differentials, and you also need to define if the differential can be locked. Now, you can create independent differentials on each axle, but you could also create linked differentials, such as is the case with the forwarder that we have in the samples. You can also simulate three types of brake. The first one, surface brakes, are the brakes you have on each wheels. So they apply a per wheel stopping force that is based on your user input, basically how strongly the user depresses the braking pedal. The per wheel stopping force can vary from wheel to wheel. Typically you'll see, for example, a stronger stopping force on the front wheels and a weaker stopping force on the rear wheels. You can also simulate the parking brake. The parking brake is a stopping force that is applied on the rear wheels based on another type of user input. Finally, you can also simulate the retarder. The retarder is not quite the same as service and parking brakes in that it's a slowing force, not a stopping force, and it is based on the friction created with the drive shaft's rotational speed. So this is something that is used typically in bigger vehicles such as trucks or dump trucks. Now, if you are modeling an automatic transmission, you will also have the parking gear that can act as a stopping force when the user selects that gear. Vortex allows you to simulate wheeled vehicles and tracked vehicles. So that means that if you have some wheels on your vehicle, you need to define mass, width, radius, but also the suspension damping and stiffness for each of the wheels. You could also choose to fully model the individual physical parts of your suspension, and that can be useful if you wanted to do, for example, a wishbone suspension. But in most cases, you can use the vehicle system inputs and outputs to achieve the proper performance on your suspension. Now, Vortex allows you to simulate tracks, which is not something that is commonly found on the market. So if you want to simulate tracks, you can select from one of two types of tracks. The first one, rigid tracks, is what you'll find, for example, on the PackButt template. In that case, you only need to define the sprocket and inler wheels, which are at the front and back of the tracks. If you are building flexible tracks, you will have to add the specifications for the road wheels, which are the wheels that are found on the interior of the tracks. Each of those wheels will also need to have a defined suspension using a torsion bar type suspension. The chassis is different from other vehicle system components so that it is mostly set in standard Vortex part. That's where you'll define the collision geometry, the material, the mass, the inertia tensor. But it is something that is part of the core rigid body dynamics of Vortex software solution. You can, however, set in vehicle system the odometer that is used on your vehicle, and you can set a starting odometer value, and then you can track the distance that has been driven by your vehicle using that same odometer. On the steering side, Vortex supports 3 steering models out of the box, plus the capacity to create custom steering models. The first one is the most standard steering model out there, the Ackerman steering model, which you find on most vehicles that are on the roads and even a very large variety of off-road vehicles. You can also select pivot and crab steering methods. The pivot steering method will angle wheels so that your vehicle can rotate around a point that is located at the center of the wheelbase, whereas the crab steering method will put all wheels in parallel and will allow your vehicle to move in a direction without rotating. Now, the crab steering method can be sometimes used, for example, on some types of forklifts. So there is one last set of components in a vehicle system, and that is the vehicle logic components. Vehicle logic components are there to link different components that are not physically linked in the simulation. For example, the braking logic calculates the amount of force to apply to wheels based on user input, vehicle speed, and the weight of the vehicle. There is not a physical link between the brake pedal and the different brakes on your wheels. Same goes for the throttle logic. There is, it communicates the throttle to engine and transmission because there is not a physical link providing that information to those two components. The engine logic allows you to control start and shut down operations, and it's especially useful if you want to simulate a manual vehicle and you want to have the possibility of simulating the engine stalling. So we're going to jump into today's first demo portion in which Marc-Alexandre is going to show us how to use presets and how to customize presets in the Vortex editor. Marc-Alexandre?
Thank you, GP. I've already opened my Vortex editor. Now the vehicle system is implemented at the mechanism level, so I'm going to use the new button to open a new mechanism file. It's a blank file here. The vehicle system is located in the upper right toolbar here, so that's the wheel icon. When you click on the little arrow triangle button, you see a list of presets appear. Click on one to insert it inside the vehicle. Now, in the 3D viewport, you'll notice that adding the vehicle system has created 4 wheels inside the 3D viewport, and has also added something called a dynamic component. The dynamic component is the list of inputs, outputs, and parameters that are used to define the vehicle system. Now, these come from the preset, and they're slightly different based on what kind of vehicle you're actually building. Let's start with the input. The inputs are values that you can set during runtime. So normally the input come from either a script, a control device such as a steering wheel or joystick. You can also set the values directly inside the dynamic component input. In this case, for a car with an all-wheel drive, we've got our Ackerman steering, so we can set it on or off by checking the box. It's receiving an input signal here. This can be connected via the connection container, which is a standard Vortex feature, to either a control system or more probably a script to filter the input from the control system itself. Other input include the automatic transmission, so you can set the damping, the gear ratio, shifting and neutral, the transition time. All of these can be set during runtime. And you can also have the lever position. So for the automatic transmission, this is going to be right now in parking. You can change it manually to D1, D2, D3, and so on if you've defined these gear ratio, or reverse if you've defined a gear ratio for that. Those are set up further down in the parameter. There's also a braking logic that's established. Again, an input signal is received here. This can be connected to a brake pedal, for example, or more commonly a script that's going to filter the signal first. You can set your maximum brake torque, and this is later sent to the wheel, and you can set individual brake scaling to the wheel. So if you set a brake scale of 1, you're going to have the maximum torque. You can change this number to change the brake torque that's applied to individual wheel. You can also set differential. In this case, we've got 3 differential, one that distribute power to differential 2 and 3, and differential 2 and 3 that are connected directly to the wheel themselves. And there's a value here that's called enable lock. If you've set your differential so that it can be locked, this will lock the differential. So for example, a military vehicle will sometimes have a lockable differential. This is where the input to lock it will be connected. The engine itself has a number of input that can be set, including an input throttle. There's a checkbox to have the engine running on or off, so you can connect this to a control, like a key, for example. You can set the shaft velocity damping and a damping exponent. And you also have entries for the wheels themselves. So the brake scale, the mass, the material, the radius. Wider radius as an input, for example, to simulate a flat tire. You can change the radius at runtime to make a smaller wheel. A recent feature that we've added is the suspension highest point and lowest point, which allows you to set the maximum travel of suspension in addition to the existing damping and stiffness. And this is set by individual wheels, so you can have a customized suspension for front and back of the vehicle, for example. There's also the throttle logic, so you can set an input for the throttle, set of input for the torque converter, so whether you want a torque converter that's locking and what set the drag for this. And there's additional input if you have a different vehicle type. We're going to look at them briefly. In the outputs, those are signals that are sent out from component. They can be used either as a display, like a head-up display, for example, or to drive a script. For example, automatic transmission will tell you the gear number and the gear index. Chassis will give you an odometer distance for the distance that's been covered since the start of the simulation, the current speed, the world axis. All of these can be used for scripting. The engine gives you a lot of data, the maximum horsepower, the max power, the torque, the current RPM, the RPM, the max power. All of these can be used to either drive a script or drive a further component. You also have outputs for each wheel, such as the angular speed, the material in contact. This tells you what the wheel is currently rolling on, and we're going to look at it a bit later on. The current steering angle and a transform. This transform will be attached to the graphic node of the wheel to drive the graphic and ensure that the wheel turns at the proper speed visually to follow the dynamic. The torque converter also has an entry for the output where you can have the torque, the RPM, the speed ratio. All of these can be used for further scripting and display. In the parameter, those are values that are not supposed to change during runtime. So for example, the shaft inertia, the shaft mass, the powertrain axis, the position. Ackerman steering, you've got the reference position, the speed of the steering system. Chassis, you can set the automator value. You set a part, as GP mentioned earlier, the chassis is defined as a part in the assembly, and that's where you connect it. You can also set the differential, whether they're lockable or not, and you can set the wheel, whether they're steerable or not. And finally, you can also set CTR table and lambda table for the torque converter simply by inserting them here. Now, if we take a look at the torque table for the engine, what it is a comma-separated value table. So basically, this is what it looks like. It's a bit easier to read if you have a spreadsheet program, but you can also open it in the text editor like this. Usually you have a description. There's a standard format. So you have a description at the top, the RPM listed in the column here, and then the throttle put up here, and then you have the RPM, the torque for each RPM level. Now this can be modified and adjusted to reflect real-world value. If you have engineering value for your vehicle, you can easily create a torque table like this. And there's also a space for a braking torque table that you can insert here in the vehicle. You'll notice that I've used the filter to rapidly find these fields. This is a very useful feature, and I invite you to use it when you work with the vehicle system. If we briefly take a look at another preset, for example, let's say the excavator, for example, you'll notice that the collision geometry that are inserted are a bit different because it's a track. There's a dynamic component as before, but now we've got also extension to drive the treads, the track of the vehicle. So there's a place to connect it to the graphic node of the vehicle, and the system takes care of animating the track for you. Now, what do the presets look like inside the file itself? You can find them inside the vehicle system folder, which is itself in the resource folder in your Vortex editor installation. You'll notice that each preset has a VXR file, and we also supply you with a number of preset torque table that you can use as a starting point or as a default point. What the preset looks like is something like this. It may look confusing at first, but once you start reading it, you realize that really it's all a bunch of modules that are connected together. For example, the automatic transmission logic here, the braking logic, and all these modules can be copied and pasted inside a new preset so that you can create the vehicle that you want to have. By dropping a new preset inside the vehicle system folder, they should appear up here in the listing if you've given them a new individual name and there's no syntax error in your file. If you don't see it appear in the listing here, it's probably because you have a syntax error of some kind in the file. You probably did like me and you forgot to put a comma or close a parenthesis somewhere. So don't feel bad about this. Back to you, GP.
Thank you, Marc-Alexandre. All right. So now that we know how to select a vehicle template and use it to add it to a mechanism, we're going to look at what the entire process into creating a Vortex vehicle is. And it's going to start like any other type of mechanism, and that is with a graphics gallery. The graphics gallery is going to define your collision geometries and the look of your vehicle. Then we're going to select the vehicle preset we wish to use. And once we've selected the vehicle preset, as you've seen, there will be collision geometries created for the wheels and the track, so we're going to connect those to make sure that our vehicle can be operated. And finally, we're going to go field by field and fill the specifications for every mechanical components. What we're going to be doing is we'll start by creating a new LAV, which is the 8-wheeled vehicle in the sample, and then we'll be looking at some differences that we have with other more complex mechanisms. So I'll pass it back to Marc-Alexandre Vezina for the meat of today's webinar.
Thank you, GP. So we're going to do a basic vehicle system implementation on the LAV, the light armored vehicle. So to do this, I've started a fresh mechanism file. And first, we're going to insert a 3D model. So I'm selecting from the top toolbar, insert graphic gallery from file, and I'm picking the LAV. There we go. And now we've got our LAV in the 3D viewport. And you can see here that there's a graphic gallery entry with the various nodes that compose the model, and we've got one for the main hull that we're going to use to create a part so that we can hook our vehicle system to it. But first, we need to insert an empty assembly. So here I'm right-clicking on the mechanism and choosing Insert Empty Assembly. You can also use the toolbar up there to add the assembly to the mechanism. And I'm going to right-click on the node for the chassis, and I'm going to use Create Part, select the assembly to create a part in the assembly, and then you're going to want to save your work. And then I'm going to add a collision geometry. Again, I'm right-clicking for speed. That's a very useful shortcut. You can also go through the toolbar, but I find that it's usually faster to just right-click on the object and just go through the speed menu. I'm adding a convex mesh. This is going to wrap the object in a mesh, so it sort of looks like a bar of soap. Normally, you can do something that's much more closer to the actual hull of the vehicle, but in this case, it's going to serve our purpose well. Now, I'm opening the part, and you'll notice that we only have the graphic node that's used in the part. We're going to set a mass property. In this case, 15 ton, and we're going to use the Compute Inertia and Come button to create the inertia tensor, which is here, so the shape is good. I could always use the Reshape button here to change the shape if I wanted to, but let's say it's good. And also, I'm selecting my collision geometry, and I'm setting it to the chassis material, so that it's like a metallic steel material. And then we save, and we can close it. And we go back to our mechanism, and now we're ready to insert the vehicle system into it. So I go here, and in the preset, there's one for an 8x8 light armored vehicle. So I insert it in the mechanism, and you'll notice that right away we've got wheels that appear inside our tire model. The position is good because in the preset we've already set the coordinates to match this particular model. Obviously, if you're doing a different type of light armored vehicle or even a different type of 8-wheel vehicle, the position might not correspond right away and you'll have to adjust it in the parameter. But in this case, they already match. So the first thing we want to do is tell the computer what is the chassis reference. So if you type part in the filter, in the parameter for chassis, there's a field called part. And what this does is that it allows us to choose the part that is the actual hull or main chassis of the vehicle. It's possible to have more than one chassis. In fact, if you look in the Vortex sample, there's a forwarder that has an articulated chassis composed of two components. So we have a front chassis and a rear chassis. In this case, I've had to define a part for both the front and the rear chassis. But here, it's simple. We've got only the one chassis. So I've set the dynamic component. I'm going to save it. Now, I need to tell the computer, okay, These graphic wheels are going to move with this dynamic wheel, and I also need to tell the computer that this dynamic wheel has a certain size, because if I go like now, I'm not going far on these little tiny wheels. So I go into my vehicle system and I type radius, and this gives me all the feel for inputting a field radius. So I'm not going to do all the wheels because there's 8 of them, so we're going to jump ahead a bit later, but I'm going to do one wheel to show you what it is. So the front left wheel now has the proper radius, and then I'm going to do the same for the width, and the width is 0.310 meter. There we go, and now we've got the proper width. You'll notice that the vehicle is oriented along the positive x-axis, and it's at the ground level. It's very important when you set your 3D model that it's oriented that way to avoid confusing the vehicle system and getting bad reference. Let's keep on going on the wheel. I'm going for the mass, so now I've got 30 kilogram, for example. And then I would repeat this for every wheel, obviously. And then we want to make sure that our wheel is steerable. So in the parameter for the front left, middle right, and right wheel, they're already preset to steerable thanks to the vehicle preset. But if they're not, simply check them to make sure that they are steerable. All right. Now, what we want to do next is to make sure that our graphic wheel are going to turn in step with the dynamic wheel. So what I'm going to do is that I'm going to go to my mechanism and I'm going to insert a connection container. Now, in the dynamic component, in the dynamic component, we've got the front wheel output. There's a transform available. So I just drag it to the output field. And now it's asking for an input. So the input for that is going to be the graphic parent transform of the front left wheel. So I go back to my connection container and I drag the parent transform to this. And now the graphic wheel is connected to the dynamic wheel. So if I go like this, you'll notice that the graphic wheel is moving with the dynamic wheel. Now I don't want to go through the whole process of doing every wheel. So we're going to just skip ahead into a vehicle that already has all its wheel connected, as you can see, and it should be ready to go. So I'm just going to use the shortcut Shift G to hide the collision geometry so that we can see the vehicle better, and we're going to start the simulation. Not quite what we want. There's something weird going on. So we're going to stop and we're going to look again. The collision geometry of the hull is intersecting the collision geometry generated by the vehicle system. So first, we need to tell the computer, okay, there's a collision rule that you need to obey where the assembly, that is the hull, that contains the hull, will not collide, so I leave this checkbox empty, with the dynamic component of the vehicle system. So in this case, we've got the vehicle group, so I check it, and I save it. And now we're going to try again. Much better. Now this time the vehicle is actually on its suspension. You'll notice that the turret is floating. The reason for that is that in the graphic gallery, the turret is not under the chassis hierarchy, and so it's not actually following the chassis. So I could technically just open the graphic gallery quickly and then grab the turret, put it under this, and then go back to my mechanism, and this time the turret would follow the chassis. So this is all nice and well. We want to make sure that we have the proper material table. So I'm looking at this. I've got defense vehicle material table, which is great. Now I want to make sure that my wheels have the right material so that my behavior on the surface contact will be correct. If I look at material, it's already preset to wheel, so it's perfect. There's also an output that says material in contact. What this does is that it tells me what the wheel is touching at any point in time. So we're going to go to the grid. I'm going to tool up here, and I'm going to set the grid to represent the road. So I'm going to apply this, click on OK. And now when I start the simulation, you'll notice that the material in contact tells us that there's a wheel that is touching the road. What this is useful for is to drive some script. For example, if you want to drive a particle emitter to create dust and you want to make sure that the dust color matches the ground, you can use this to know what the vehicle is rolling on at this particular point in time. All right, so now that we've got the vehicle ready to roll, we're going to try and make it move a bit. So we're going to go into Engine, and we want to make sure that the engine is running, obviously. And then we're going to need to give it some throttle. Now I'm doing the input manually, but obviously you could do this through a device or a script. And then finally we need to put the automatic transmission in gear. So automatic, we're going to drive position 1. There we go. And then we're going to click on simulate, and the vehicle is moving forward. And you'll notice that the suspension is actually active. Well, this is looking great. It's not bad, but we could be better. If we had a proper torque table, we'd get a more accurate behavior for the engine. So we're going to look for torque, and we've got the torque table file here. So I'm going to click on the little button here. I'm going to select the torque table, and I'm going to insert it. And also have a space for braking torque table. So I'm going to take another comma-separated value file. I'm going to insert here. And now when the vehicle runs, the behavior of the engine is a lot more realistic. Well, this is great. Now, normally at this stage, I would add scripting to control the various components, add control systems such as steering wheel or a joystick, and connect them to the script, which is itself would drive the input of the component. I could also add camera extension for the lights and so on. But that's a little beyond the content of this webinar. But one thing we can do is add the vehicle to a scene and see it in action. So I've opened a basic scene from the sample. I'm right-clicking on the scene itself, and I'm telling it insert a mechanism from file. On the right-hand property panel, I use open resource. So I've got the LEV in progress. So I click here, and now it's being inserted into the scene. And we're going to use the move tool to place it on track like this. And then we're just going to have the scene run. And there we go. So now the vehicle is rolling. And you can see that the suspension is actually responding to the environment. If you go inside your mechanism here, and you go into the dynamic, and you go into material, you're going to see the material in contact right now is sand plus wheel. And when the vehicle reaches the tarmac here, this is going to change to sand, to road plus wheel, actually. So if you had a particle generator, for example, that's generating dust behind the vehicle, and obviously in the real world, as soon as you get on pavement, the dust stops being emitted, this is how you control it. So if we go here, we can see the vehicle is coming here, and then it's going to change to road plus wheel. And I can also have input steering here. If we change it a bit, so if we go here, we're going to see if we can make the vehicle turn a bit. So input steering 0.5, then we go back to our scene. And then we launch it. And now we've got our vehicle slowly turning. I would need to put more input into that to get a proper reaction. Now, let's look at other types of vehicle. This, for example, is a tracked vehicle. So we've got the vehicle system here. It's a vehicle with 4 tracks, so 1, 2, 3, 4. So it's got 4 extension for animation. This was built into the preset. You've got your dynamic component with your input, output, and parameter. Now you'll notice that we've got a left electric motor and a right electric motor. So we've got actually two motors in that specific vehicle system. And let's check if I've got the grid. Let's give it some road. And let's see if I've got, yep. So we can see that the tread is actually moving. And we can do fancier things like this and with the treads themselves. Now you can do more complex vehicle system than this. If we go into the forwarder, for example, so if we look at the forwarder and we open the vehicle system, it's got a dynamic component. Now the forwarder has a front chassis. It's got bogies to connect the wheels to the main chassis. So all of this has been defined as a sort of miniature chassis part inside the vehicle preset. And we've defined a rear and a front chassis, and they both have their own part reference. And this creates a very complex vehicle built entirely using a preset that's being modified using elements from other vehicles. For example, the hydrostatic transmission is the same as the excavator. The wheels are similar to the one from the 8x8 LAV, and that way you can build your own preset exactly according to your needs. Back to you, GP.
Thank you, Marc-Alexandre. All right, so before we move on to the questions, we have one last section we'd like to go through, and that is a discussion on how you can combine vehicles with Vortex cable and earth-moving simulation module. Now, the cables in Vortex allow you to winches, pulleys, cables, and chains to a mechanism. So that opens up a bunch of very interesting advanced simulation scenarios, such as simulating towing operations or simulating heavy equipment such as mobile cranes. By having Vortex vehicle combined with those cable mechanism, you get to actually simulate the entirety of the operation and not just different early or later portions. You get to drive your LAV, for example, in this case, to the vehicle that needs to be retrieved, and you get to actually load the vehicle on a truck. You could also drive the mobile crane to the proper position, learn to position the mobile crane before accomplishing lifting operations. If you're not familiar with Vortex cable systems, you can have a good look at its capabilities in our March 2016 webinar, which is available on our YouTube channel at youtube.com/vortexsim. Similarly, you can combine Vortex vehicle systems with Vortex earthwork systems. That allows you to simulate heavy equipment, earth-moving equipment, and actually operate them into their workplace. And that means driving the vehicle to the work site, through the work site, and then actually doing the scooping and unloading operations from start to finish. We've also had a Vortex Earthwork Systems webinar in April of this year, and you can also find it on our YouTube channel. Now, before we open up the question, I'd just like to do a quick recap on today's presentation. What we looked at today is how Vortex Vehicle Systems allows you to create vehicle simulations that use engineering-based specifications, and allows you to create very realistic tracked and wheeled vehicles, and you can deploy them into a highly realistic environment in which you can actually discover emergent behavior dynamically. Vortex Vehicle Systems can be combined with existing Vortex modules to allow you to create more complex training or virtual prototyping scenarios. So we're going to move on to questions. You can send us your questions using the right-hand side questions box on the GoToWebinar interface. You can also download the presentation materials and handouts in the handouts section. And if you are leaving us at this time, I'd like to thank you for joining us today. We'll be sending a recorded copy of today's webinar early next week by email. We hope you'll join us for our next webinar, which will be on September 8th, and will be the first of a two-part webinar series on troubleshooting simulations with Vortex Editor. This first part will focus on the contact and collision geometries display in the Vortex editor, and then the second portion will focus on other debug displays available. Thank you again for joining us today, and we hope we'll see you in September.